Hi, everyone, and welcome to this episode of Crowded Beaker Solves. Today, we're continuing our series on chemical kinetics, specifically using the method of initial rates to determine the rate law for a reaction. I already have an example set up that we're going to get into, but I hope you'll stick with me on this episode because we're going to have a couple of pause the video moments, including one that includes a little bit of a wrinkle, a little bit of a challenge that you may see once in a while. And I thought I should warn you about it because chemistry professors and textbook authors love to throw this in there. So let's go ahead and get started. We have a reaction up here, and I'm looking for the rate law, which is going to be set up in the form of rate equals K times the concentration of NO, which is one reactant, raised to some order. I don't know that yet. And oxygen raised to another order. Again, I don't know that yet. But what I want to do is, with this method of initial rates, you want to pick two trials where one is being held constant while one is changing, and you can see the effect of the change on the actual rate. All right, and we're going to quantify that. So while I'm looking at it, I might as well start with trials 1 and 2 because the oxygen is changing and the rate is changing. So let's do that first. So let's do rate 2 over rate 1. Again, I'm just trying to show you how you should set it up. This is sort of the traditional way of doing it so that your grader or your professor knows exactly what you're doing and that you know exactly what you're doing. And so everybody's happy with that. So we're going to plug in our concentrations. In this case, for the NO, it's 0.02. Sorry, I missed a zero. Once in a while that happens. The zeros are important. And it's raised to the x. And I don't know what x is, but that's okay because that's going to cancel anyway, along with the constant. 0.020, and that's going to be raised to the y. 0.010, and that's going to be raised to the y as well. So this number divided by this number is not exactly 2, but it's really close to 2. It's just a hair over 2. And so when you get a number that's really close to a whole number, just round it. So 2 equals, and this is 2 twice as big, 2 to the y, and therefore y equals 1, and that's first order. Okay, so I've just figured out that the y exponent up here is a 1, a first order. And then I want to do the same thing with the other one. And I think I'm going to do trials 4 and 2 because here we have a change and that stays constant. There's extra trials that you don't actually need. Sometimes that happens and you just have to not let it bother you. So let's do rate 4 over rate 2. And we'll take a minute and plug that information in. And we'll put the constants in. And the concentrations here are 0.040 and 0.020 raised to some x value. We're just calling it x. You could use any letter that you want. And then the other one is 0.020. It takes a little time, and some people are kind of allergic to spending extra time on things that they don't feel are necessary because they know that's going to cancel anyway. But try to just take a moment and do it so that your grader is happy. And we are scientists after all, and we want to show our work. So I get to this point. This number, I did the math, is not exactly 4, but it's like 3.98. That's close enough. So I'm going to call that a 4. And this is a 2. This divided by this is 2 raised to the x. So 2 to the something has to equal 4. X must be 2. And so that it's second order. So we've got a second order and a first order and a third order overall. Okay. Now, related question, and you're going to be asked this question quite a lot. The question that is next on the list, typically, is what is the value of the rate constant? Like, what is that number? We know there's a constant in there, but what is it for this reaction under these conditions? I'll say it again. Every reaction has its own unique rate constant under whatever conditions it's in. And if those conditions change or the reaction changes, the rate constant changes. But in this example, what is it going to be? So how would we do that? Well, what we're going to be doing, it's actually pretty simple. We've done most of the work. And because we found out what the orders are. And what we can do is basically go back and pick a trial. it really doesn't matter which trial you pick. I'm just going to pick the number 1 trial because it's just easiest, and it's right there. And actually simply plug it into the rate law that I've already determined. So trial 1, I'll make a little note that it's trial 1. And I'm going to go ahead and say, all right, well, the rate in trial 1 was 0.028, and that is moles per liter per second. Now, I didn't use the units up here. I was just kind of doing the math on the side. But here I'm going to actually put the units because they are important. This constant has to have a unit on it. And we want to express that unit properly. So then we're going to put in 0.020, and that's in moles per liter, but that's going to be squared, and 0.010 moles per liter, and that'll be to the 1, and I'll put the moles per liter there as well. And once we pick a trial and we plug that all in, we know the exponents now so that we can do our math, okay? And when we do the math, we end up with a k value of 7,000. Okay, so I take 0.028 divided by 0.02, divided by 0.02 again, divided by 0.01, and I get 7,000. And that's great. You're going to get a number. It could be really big. It could be really small. But you will have to put a unit on it. And this is where people get, you have to be nitpicky about things. So we want to know what the unit has to be so that moles per liter per second and moles squared per liter squared and moles over liter here are all going to cancel as much as they possibly can. Okay, and this can get a little messy, but try to follow along. Over on this side, would you agree that we have basically moles cubed over liters cubed on that side? Because we have those and those. And over here we have moles and liters only once, and then we have the time component. Now, to get this side cleared off by itself and get k by itself, I'm actually going to have to multiply both sides by liters cubed over moles cubed. When you divide both sides by a fraction, you end up multiplying by its reciprocal, which is liters cubed over moles cubed. And in that case, one of the liters is going to cancel, leaving a remainder of 2 liters squared. One of the moles is going to cancel, leaving moles squared. And my remaining unit is liters squared over moles squared seconds. Okay, and it's a goofy unit. Try not to let it bother you. But you will have to practice getting that unit based on the units that you have over here. And pay attention to the time unit. Sometimes that gets a little wacky if it's in hours or centuries or decades or whatever it happens to be in. So there's my example. Now, for our first pause the video moment, I have a second example. And I will set this out right here. And if you feel so led, please take a moment and pause the video and see if you can find the appropriate rate law for this reaction. Rate equals a constant times CO to the something and NO2 to the something. Pause the video and see if you can do it. All right, I'll take a second and show the solution to this one. And congratulations if you found that the reaction is first order with respect to both reactants. I did the math. I compared rate 4 over rate 1 and rate 2 over rate 1. You may have picked something different, and that's okay. But you should end up, no matter which way you pick, that it's first order and first order. And so the rate law is rate equals a constant and first order. And the rate constant that I used trial 1 again. I plugged all the numbers in just the same way as I did in the last example, and I got 1.9. But because there's only 1 mole or 2 moles per liter on the right and only 1 on the left, only the one of them canceled, and we only have 1 left over, liters per mole, hours. Pay attention to the time unit. It was hours this time, and that would be the answer for that. Oh, sick. Okay, so we're going fast. Congratulations if you got that. And I wanted to show you one more example. This one. And we'll do another quick pause the video moment. And you can pause the video if you'd like and try to find the orders of reaction for A, B, and C. This one actually has 3 reactants on it. Take a moment, pause the video, and I'll show you what I found out about this. All right, and if you were able to do it, congratulations. Let's go ahead and show you what I found. Now, this one had a little bit of a wrinkle. Now, if you got to this point and said, oh my gosh, this is getting too complicated, I better hit unpause, that's fine. We're not judging. But if you were able to get it, then congratulations on that as well. So what I did when I worked out this solution, I found out that A was second order because comparing rate 4 to rate 3, it went up by a doubled, but the rate went up by 4. So that's a second order reaction. For B, I found out that it was a first order reaction, comparing rates 3 over rate 1, in which had this changing, going up by a factor of 3, and the rate went up by a factor of 3. So that's great. And then you might have gotten to this point and started panicking because there's no 2 trials in which C changes, but everything else stays the same. Did you notice that? You only have one that's different, but B has a value, but it's not the same in any of the other trials. So we get to this problem where it's like, oh my gosh, panic. So what do? Well, first we take a deep breath and we say to ourselves, you know what, as long as I know the other 2 exponents, the orders, I'm okay. The math is a little more annoying, but that's all right. So what I did was I picked rates 2 over rate 1. Okay. And I put in the rates, I put in the concentrations, I put in the different concentrations here, but that's okay because it's a 1 and a 1, and the different concentrations here. And then I had to simplify it. So this was double, the constant canceled, the 0.1 canceled, and now I have this over this is 2 raised to the 1. I know that's a 1 now. And this was 1.5 raised to some z value. We don't know what that is. But because 2 raised to the 1 is just 2, and 2 is over here, and if I divide both sides by 2, I get 1 equals 1.5 raised to the something. Now, again, what's going on? So 1 equals 1.5 raised to the something. How does that work? Well, the only thing that satisfies this is the fact that 0 or z must be a 0, because any number raised to the 0 is simply 1. Doesn't matter what this number is. If that's a 0, this is going to be 1. And so for C, it's actually 0 order with respect to C. Okay, that was a tricky one. But as long as you know all of the exponents except 1, you can pick any 2 trials, throw them in, and the math should work. It might just be more annoying than usual. And finally, to find the rate constant, I plugged in I used trial 2 on this one. And the rate, the concentration, this one was squared, that concentration, and then this one basically became a 1, so I just kind of ignored it. And I got a rate constant of 5.0 times 5.0 liters squared over moles squared seconds, or 1 over molarity squared seconds. This unit was moles per liter, but because it was raised to the 0, it goes away, and that's it. So that was a tricky one. And I'm hoping that you won't see too many of those, although if you spend a lot of time in the chemistry lab or in your chemistry travels, you're going to see something like that, and I wanted to warn you about those tricky ones. So if you have any questions or comments, send them to me. If you have any suggestions of problems you'd like me to solve, that's great as well. Send those to me. In the meantime, happy solving and have a great day.